We are on a collision course with the massive Andromeda Galaxy, a collection of several hundred billion stars. This collision will lead to a dramatic merger, altering both galaxies in significant ways. Andromeda, a key galaxy in our understanding of the cosmos, has played a crucial role in shaping our perception of the universe. It was Andromeda that first revealed that the Milky Way was not the center of the universe, which changed our understanding of our place in the cosmos. For over a century, Andromeda has been a focal point for astronomers. Even though much has been discovered, recent advancements in space exploration, such as the James Webb Space Telescope, have revealed new, astonishing insights about Andromeda that were previously unimaginable. Over 100 years ago, the Milky Way was thought to be a faint band of light stretching across the night sky, with limited technology preventing the resolution of individual stars. Early theories placed the Milky Way at the center of the universe, but this idea began to change in the early 17th century when Galileo Galilei used his telescope to observe that the Milky Way was not just a band of light, but a vast collection of stars, planets, and celestial bodies. His discoveries shattered the belief that the Milky Way was the center of the universe, revealing it instead as a sprawling group of stars. In 1750, English astronomer Thomas Wright proposed that the Milky Way was a flat disk of stars, including our solar system. However, his hypothesis was limited by the technology of the time. By the 1900s, significant breakthroughs in astronomy occurred. In the 1920s, Edwin Hubble used the Hooker telescope at Mount Wilson Observatory to prove that distant nebulae, including Andromeda, were separate galaxies, each containing billions of stars. This discovery fundamentally changed our understanding of the universe. The Andromeda Galaxy, also known as M31, has been known since at least the 10th century when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud. Al-Sufi's keen eyesight allowed him to identify Andromeda without the use of advanced instruments, which is possible because Andromeda is one of the few galaxies visible from Earth without a telescope. In 1612, Simon Marius made the first telescopic observation of Andromeda, paving the way for future astronomers. In 1764, Charles Messier catalogued Andromeda as M31, further solidifying its place in astronomical research. A major leap in understanding Andromeda came in 1864 when English astronomer William Huggins studied its spectrum and found it to be different from that of typical gaseous nebulae, a crucial observation. Andromeda is massive, with an estimated mass between 1 and 2 trillion times that of the Sun, and is thought to be about 10 billion years old, suggesting it has evolved through the merging of smaller protogalaxies. Early astronomers believed Andromeda was much larger than the Milky Way, but recent studies have revised these estimates, showing that the two galaxies are much closer in size than previously thought. Andromeda's physical size is larger than the Milky Way, with a diameter of about 220,000 light-years compared to the Milky Way's 100,000 to 175,000 light-years, emphasizing its vastness. One of Andromeda's most fascinating features is its active galactic core, which is powered by a supermassive black hole with a mass between 110 and 230 million times that of the Sun. Observations with advanced telescopes, such as the Hubble Space Telescope, have revealed two bright spots near the galaxy's center, indicating powerful gravitational interactions and the presence of this enormous black hole. Andromeda also hosts a large number of globular clusters, about 460, each containing hundreds of thousands to millions of stars. This abundance reflects Andromeda's history of galactic cannibalism, where smaller galaxies were absorbed, contributing to its star population and diversity. Recent observations suggest that Andromeda may be transitioning from a typical spiral galaxy to a ring galaxy, characterized by a ring of young, bright stars. These ring galaxies can form through galactic collisions or when a smaller galaxy passes through the center of a larger one, making them unique in the universe. The impending collision between the Milky Way and Andromeda, expected to begin in about 4 billion years and unfold over the next 2 billion years, will be a momentous event in the cosmos. This grand collision will result in the formation of a new supergalaxy, nicknamed Milkomeda by scientists and enthusiasts. The merging process will be marked by intense gravitational interactions and tidal forces, significantly affecting both galaxies. As the Milky Way and Andromeda draw closer, their immense gravitational forces will begin to distort their shapes, pulling stars, gas, and dust from both galaxies. This will create elongated tidal tails and trigger a series of complex gravitational interactions. The merger will not be a smooth process. Instead, it will be chaotic and dynamic as the two galaxies slowly merge, tearing apart and reorganizing their structures. One of the most spectacular outcomes of this collision will be the birth of new stars, resulting from the interaction of the two galactic bodies. The merging of galaxies, such as the Milky Way and Andromeda, will significantly impact the creation of new stellar populations, as gas and cosmic dust are compressed, sparking the birth of new stars. This cosmic collision will not only affect the outer appearance of the newly formed galaxy but also its internal dynamics. Gravitational interactions among the stars and gas clouds will cause a rearrangement of their orbits and velocities. Some stars will be ejected into more erratic paths, while others may be completely expelled from the system, becoming rogue stars drifting through intergalactic space. At the heart of both the Milky Way and Andromeda lie supermassive black holes, and their interactions will play a crucial role in shaping the outcome of the merger. These behemoths, each millions to billions of times more massive than our Sun, will spiral toward each other due to the gravitational waves generated as they draw closer. The final stages of their merger will be catastrophic, releasing vast amounts of energy in the form of gravitational waves and radiation. This event will give rise to a single much larger black hole at the center of the new galaxy, surrounded by a rapidly spinning accretion disk of gas and dust. The presence of such a powerful central engine will have profound implications for the galaxy's evolution, influencing star formation and the behavior of gas and dust, possibly triggering quasar-like phenomena as matter falls into the black hole, emitting intense radiation across the electromagnetic spectrum. On a larger scale, the merger between the Milky Way and Andromeda will contribute to the ongoing evolution of cosmic structures in the universe. Galactic mergers are essential processes in the hierarchical model of galaxy formation, where smaller systems combine to create larger, more complex structures over time. Studying such cosmic collisions provides valuable insights into the mechanisms driving galaxy formation and evolution. By observing how stars, gas, and black holes interact during these events, astronomers can test theoretical models of galaxy mergers and refine our understanding of the underlying processes at play. The merger will also have implications for the distribution of dark matter in the new galaxy. Dark matter, an invisible and elusive form of matter that accounts for much of the universe's mass, plays a vital role in shaping the structure of galaxies and their gravitational interactions. During the merger, the dark matter halos surrounding the Milky Way and Andromeda will interact and merge, altering the overall distribution of dark matter in the new galaxy. Studying the effects of dark matter during and after the merger will provide critical clues about its nature and properties, helping scientists unravel one of the greatest mysteries of modern cosmology. Additionally, the Milky Way-Andromeda merger will offer a unique opportunity to study the formation of cosmic groups and superclusters. These massive structures, composed of multiple galaxies bound together by gravity, are the largest known entities in the universe and provide insight into the large-scale distribution of matter and the evolution of cosmic web-like structures. As the two galaxies merge, their respective satellite galaxies will also be affected, either merging with a new supergalaxy or being destroyed and absorbed into its expanding halo of stars and gas. The fate of these smaller galaxies will depend on their orbital dynamics and speed relative to the merging Milky Way-Andromeda system. Some may survive largely intact, becoming dwarf galaxies within the new supergalaxy, while others will be disrupted and incorporated into the larger structure. The merger will also have consequences for the environment around our solar system. While the collision itself poses no direct threat to Earth, the gravitational disturbances and the influx of radiation from the merging galaxies could subtly affect our planet's atmosphere and radiation exposure over geological timescales. Furthermore, the creation of the new supergalaxy will dramatically alter the night sky for any future inhabitants of the Milky Way. The merger will change the positions and distributions of stars, star clusters, and nebulae, potentially forming new star groups and cosmic landmarks that will shape the cultural and navigational aspects of any civilization that emerges in the distant future. In conclusion, the merger between the Milky Way and Andromeda represents an awe-inspiring astronomical event on an immense scale. This process will transform both galaxies, creating a new super-galaxy that integrates the material and characteristics of its predecessors into a unified whole. From the reshaping of spiral arms and the formation of new star clusters to the merger of supermassive black holes and the redistribution of dark matter, every aspect of this cosmic collision will leave a lasting imprint on the future development of the local galactic group. Studying this event offers astronomers a unique opportunity to witness the power of gravitational interactions in shaping the universe we inhabit, highlighting the dynamic and ever-changing nature of cosmic evolution, where galaxies collide, merge, and give rise to new structures and phenomena that continue to inspire wonder and curiosity in our exploration of the cosmos. As the cosmic systems collide, the gas clouds within them will collide and compress, leading to the formation of new stars. These star-forming regions, or stellar nurseries, will experience intense gravitational forces, forcing the gas to break down and trigger the birth of new stars. These newly formed stars will often group together, advancing the creation of a new supergalaxy, complete with fresh stellar populations. At the same time, the gravitational chaos will disrupt the orbits of existing stars. Stars that were once in stable orbits within the Milky Way or Andromeda may be flung into new elliptical paths or, in some cases, ejected entirely from the merging system, becoming rogue stars unbound to any galaxy. This rearrangement of cosmic material will contribute to the formation of new astronomical structures and may result in complex star streams and clusters, blending the remnants of both galaxies. In addition to new star clusters and star formation, the merger will also lead to the creation of vast new structures within the newly formed galaxy. The gas, dust, and cosmic debris from both the Milky Way and Andromeda will mix and coalesce into new configurations, forming enormous regions of star formation, spiral arms, and possibly new cosmic features that are a blend of both galaxies' original forms. These structures will evolve over time, influenced by the dynamics of the merged system. The supermassive black holes at the centers of both the Milky Way and Andromeda will also play a pivotal role in the merger. As the galaxies collide, their central black holes will eventually merge into an even larger supermassive black hole. This black hole will become a powerful source of energy, dramatically impacting the surrounding cosmic environment and contributing to the dynamic nature of the new galaxy. In the end, the merger between the Milky Way and Andromeda will result in a completely transformed cosmic landscape. The new supergalaxy, likely named Mila, will be a massive entity composed of the combined materials from both parent galaxies. It will feature a rich tapestry of new star clusters, rearranged stellar orbits, and restructured cosmic elements. This process of astronomical evolution, driven by the collision and merger, will shape the future of the local galaxy group and offer a fascinating glimpse into the long-term dynamics of cosmic interactions. The merger will significantly alter our night sky and the environment on Earth, potentially impacting ecosystems, biodiversity, and the planet's climate. However, this event will occur long after humanity is gone, as our sun will evolve into a red giant and render our solar system inhospitable in about 5 billion years. The merging of Andromeda and the Milky Way raises questions about the fate of our solar system and the formation of new cosmic structures, potentially creating habitable zones for new forms of life, though vastly different from anything we know today. The new Mila galaxy will stand as a testament to the dynamic and ever-changing nature of the universe. The anticipated collision between the Milky Way and Andromeda, predicted to occur in about 4 billion years, will be a cosmic spectacle on an unimaginable scale. It will mark the climax of a gravitational dance that began billions of years ago, when these two enormous galaxies first began their inevitable approach toward each other in the vast expanse of space. As the merger progresses, one of the most significant changes expected by astronomers is the transformation of the two galaxies' spiral structures. Currently, both the Milky Way and Andromeda are spiral galaxies, characterized by their prominent arms extending outward from a central bulge. These spirals are defined by the rotation of stars and gas around a central core, creating recognizable patterns seen from Earth. However, as the galaxies draw closer, their mutual gravitational attraction will distort their shapes, stretching and pulling their spiral arms into elongated, flowing features. These newly formed tidal streams, composed of stars, gas, and dust pulled away from their original galactic orbits, will create a stunning and chaotic display across the galactic scene. The impact will also trigger intense bursts of star formation in the newly forming supergalaxy. The interaction of gas clouds from both galaxies will compress and heat up, leading to the formation of massive, glowing star clusters. These clusters will become nurseries for young stars, whose energetic radiation will influence the surrounding environment and drive the evolution of the newly formed galaxy.